A lot of people ask me to do calculus in area, so here it is. We'll start with the horizontal line first. So let's say we want to know the area underneath this line. We pick two endpoints, a lower bound and an upper bound, and we want to find the area underneath our line in between our two endpoints. This stopped at the x-axis, and there's a reason for that. If we didn't stop at the x-axis, it would go down forever and the area would just be infinite. So we need to have it stop somewhere, and the x-axis is a logical place for it to stop. If we want to know what the height is here, it's just going to be our function value at each of these values of x. The area of this is just a rectangle, which is base times height. Now, what if we wanted to find the area under a curve? We don't have any formulas from geometry for this. Let me use a rectangle to make an estimation. So I set the height of this one to be the height of my left bound. We can tell this isn't very accurate. It's an underestimate by quite a bit. I can cut it into two pieces and start using two figures to estimate it. Now I've gotten closer. This is the base of our first rectangle. This is the base of our second rectangle. This is the height of our first rectangle, and this will be the height of our second rectangle. So our estimate for the area would be the area of this first rectangle, b1 times h1, plus the area of the second rectangle, b2 times h2. And we can write this in sigma notation as bihi. That way the I can change from 1 to 2. We'll start at I equals 1, and we stop at I equals 2. These are two ways to say the same thing. Next, let's do four rectangles. Here are all the bases, and here are all the heights. To add all these up, it will just have four of them, or we can change sigma notation and make this a 4. We can do it again with 8 rectangles, which would make 8 here, or change this to an 8. We could do it with 16, which would add up 16 of these, or change our sigma notation to a 16. This shows the advantage of sigma notation. This takes up way less space than this right here. So let's get rid of all this stuff. Let's look closely at the bi. If this right here is base I, the left side would then be xi, and this right-hand side would be x sub I plus 1. It's one more than this I. If we want to know how big bi is, it's the difference between the two x's, and we call that delta x. Let's change this bi to delta x. So now let's talk about the height. This height hi, since this stops when it hits our function, the height is actually defined by the function value right there. So we would say f of xi. So we can change our hi into f of xi. Now let's move this delta x to the other side. Let's change this 16 to n so we can get any number of rectangles we want. And if we take the limit as n approaches infinity, we'll get closer and closer to the exact area under that curve. We've come up with new notation for this that visually mimics that smoothness. This right here gets rewritten as the integral symbol, which is much more smooth. This f of xi doesn't make sense anymore because it's discrete jumps. We want it to be smooth, so we're just going to say f of x. And the delta x, we also have a smooth way of expressing this as that distance goes to 0. We call it dx. And this is an integral. Areas are equal when we do the integral. As we chop it into infinite pieces, we find the exact area. That's the end of this video. If you guys want to learn how to calculate these integrals, please follow me and I will have more videos coming out. You guys are awesome. I'll talk to you soon. Bye.